I welcome you all for the technical lecture from NCTS. This is the ultimate lecture in the series of 3 lectures on basic metallurgy and inoculation. And Mr. Madhav Athavale will take us through this very interesting topic of understanding of inoculation in cast iron.
Today's topic is understanding basics of inoculation in cast iron. And what we will look at is we will again start with casting by needs and microstructure. Then we will have a quick look at what is the structure of liquid cast iron. Because while preparing for this lecture, I found that this was something interesting which I was able to find in the recent work which has been done. Then we will look at the undercooling and nucleation and the growth. We'll look at role of inoculation and requirements of inoculating materials. What is fading of inoculation, types of inoculant and their selection, techniques of application, typical casting defects related to inoculation activity. So it's a wide portion which I want to cover. I hope I'm able to cover it in the 1 hour 15 minutes that we have. Now, casting specifications and microstructure. Why I always start the presentation with this slide is I want all of us to stay anchored with why we make the castings. And it is to meet the specifications of the clients. They want dimensions, they want properties, and they want it at a cost. The dimensions come from mold and core. Microstructure is what decides the properties, and the overall efficiency of the production process gives the cost of making the casting. And as an example, I've picked up the same example that I used for gray iron metallurgy, engine block. And here, the typical specifications were a tensile strength in specific areas of the casting, and then the hardness levels which are required. And to get these properties, what are the microstructural characteristics? So those of you who have attended the earlier lecture, they would recognize this, that we want pearlitic matrix, we want ferrite less than 5%, we want graphite type A, 4, and very low quantities of B and D, and free carbides less than 1%. So how do we go about getting this? And that's where I go back to this slide, that what is cast iron, and while all of you are familiar with this, what I would like from inoculation point of view, what I would like to highlight is that it is unique because it has got double phase diagram. So it permits carbon to form either graphite or it can come out as iron carbide, APC. And foundrymen, metallurgists have to manage the structure of the iron, shape of the graphite, and the matrix so as to get the required properties. Because of these 2 points, I'm just putting here this double phase diagram, because this is very, very crucial for understanding the nucleation and inoculation process. As many of you would be familiar, in this section of iron carbon diagram, which covers only cast iron range, you have these dotted lines shown here, which represent the, so to say, graphite lines, while the solid lines below are Fe3C or cementite or carbide lines. Now, when the iron is solidifying, how the carbon will come out is decided by the chemistry of the melt, the cooling rates in different parts of the casting, and the nucleation levels or inoculation that is used to encourage carbon to come out in the form of graphite. This particular double eutectic has a particular significance. Before we get into that, a quick look at what are the phases present in typical cast iron microstructure. You will have cementite, and that forms due to undercooling. That's why I have highlighted that. It forms due to undercooling. Then you have graphite, which is a soft phase that forms by either homogeneous or heterogeneous nucleation, which we also call as inoculation. Then you have ferrite, which is a soft phase, and you have a pearlite, which is alternate lamellae between cementite and ferrite. That is, when the austenite cools below 723 degree eutectoid temperature, then these transformations will be happening. So please remember these words: undercooling and homogeneous and heterogeneous nucleation, which is also known as inoculation. So proportion and shape of constituents, they decide the mechanical properties that will be achieved in a given casting section. Let's have a quick look at what is the structure, atomic structure of liquid cast iron, and then look at its solidification. The information I'm presenting is taken from an excellent review paper, a summary paper done by Mr. Stefan Skew from Ohio State University, paper published in 2017. Upon melting of graphitic cast irons, we are starting from melting of the charge. The graphite will dissolve if enough time at superheating temperature is allowed. The structure of liquid iron is a function of its chemistry, temperature, and holding time in the liquid state. Now, X-ray analysis has been done, as well as I think neutron diffraction analysis also has been done. And it has demonstrated that the graphite is present in undissolved form immediately after melting with a size of 36 to 38 nanometers. And on holding for 5 to 6 hours at 12-20 degrees, it comes down, and the graphite gets completely dissolved after approximately 11 hours. The point I am making, the point that I draw from this particular bullet says that the graphite stays in the melt in undissolved form for a good bit of time. That's the point I am trying to make. Now, liquid iron carbon alloys with high carbon content, that is exceeding 3.5% carbon, are colloidal dispersed systems with carbon clusters in liquid solution. And the nature of the carbon clusters is not clear. There are two hypotheses. One is that they are Fe3C molecules, or they can be carbon molecules, the grouping of carbon atoms. Now, different researchers have in different ways have measured this, and the activity measurements show that the short range order is very similar to Fe3C. What is meant by short range order is over a shorter distance. We are talking about atomic distances. They appear to be similar to Fe3C, while some other researchers have reported that carbon clusters contain approximately 15 atoms, and they have a short-term stability for a short-term time period. Because in a molten ion, when there is a big movement happening all the time, it is liquid after all, then there will be a dynamic equilibrium and there will be diffusion happening in the melt. But still, what is important to note is that in some form, that is either in Fe3C or as carbon molecule aggregates, there are concentrations available. That's why I said note the likely presence, because this is an hypothesis backed by some amount of experimentation. So both carbon or Fe3C type of clusters are available, which to my mind also hints at the double nature of the phase diagram of iron carbon system. Now let's look at what is undercooling and nucleation. Now these are the two basic phenomena which happen not only in cast iron but any metal which is solidifying. And undercooling has to happen for the formation of nuclei, and they have to become stable. And then on growth, they will become solid. Let's look at undercooling. A liquid cannot solidify unless some undercooling below melting temperature occurs. Now, there are 5 different types of solidification undercooling which have been identified. But as far as cast irons go, it is constitutional undercooling and curvature undercooling is what matters. The others are not that, the effect of others is not that big. So let's look at what is curvature undercooling. Imagine a bath of molten iron and a nucleus is trying to form. So when a discrete liquid volume becomes solid, a newly formed solid liquid interface requires an increase in the energy of the system because there is interface energy associated with it. Now, for solidification to proceed, for that nucleus, for that solid to remain stable, additional undercooling is required because that is what would provide them this extra energy which is required for formation of the stable nucleus. Larger the curvature, smaller the radius, larger will be the undercool. I am not getting into too much of details on this, except for saying that thermodynamically it is necessary that undercooling takes place so that energy is available for formation of stable nuclei in the liquid iron bath. Now let's have a quick look at constitutional undercooling. And on the left hand side you see what looks like iron carbon diagram, some portion. Now during our solidification, the solute is rejected here, solute is carbon, it is rejected by the solid. So if we have this particular composition Cl, the initial solid will have Cs as the amount of C in it, which is lower than the Cl. So as the solid comes out, excess C is getting released in the melt which is remaining there. So because of the solute rejection, a boundary layer near this nuclei which is formed, the particle which has formed, that boundary layer becomes richer in solute than in the bulk liquid. And this process continues as the solidification goes from this point downwards. So as the first solid comes out, more and more solute is getting into the remaining liquid. So its composition changes. And then what is the effect? The consequence of this phenomena is that liquidus temperature is low next to the interface. That is, in this graph, you see the Cl level. Cl, that is the, say, carbon at that particular, in that boundary layer, is much higher than the average carbon in the liquid. And what it means, and then the carbon level drops and goes to the bulk melt composition. Now there is a flow of heat which is simultaneously happening, and that is indicated by this Gp. This is the gradient, temperature gradient. As the heat is being drawn towards the mold side, towards this side. Now as this solute becomes richer in the remaining solution, the solidus temperature line goes like this, which has got a gradient which is higher, which means what is resulting is immediately next to the boundary, next to the grain surface, solid liquid interface, there is a zone where there is what we can call as a constitutional undercooling. And so the overall effect of both of these, the curvature undercooling plus the constitutional undercooling, is that if the inherent nucleation levels in the cast iron belt is low, now I'm talking about cast iron, then a large undercooling is required for the formation of stable nuclei. And since the number of nuclei are less, the microstructure will have less number of large grains, because less number of nuclei, there is more scope for growth. So only few grains, but large grains. But that means lower strengths. Another effect is if this undercooling is so large that the ion temperature dips below the carbide eutectic temperature. We saw that iron carbon diagram has got two types of eutectics, either carbide eutectic and a graphite eutectic, which we saw in the phase diagram. And generally the carbon eutectic, graphite eutectic, happens at higher temperature as compared to carbide. And if the undercooling is large, then what may happen is the metal or portion of the metal goes below the carbide line, and you start getting carbides into your microstructure. And to avoid that, then what do we do? I know I'm just putting this graph just to show what happens when the level of undercooling is very, very high, because rate of cooling is another factor. So when there is a low nucleation level, there is a big drop in the temperature accompanied because of this undercooling. And then the metal may cross this white iron, the carbide eutectic line, and you will land up with, especially if the section thicknesses are small, fast cooling is happening. Instead of gray iron, you will get white iron. While if it is slow cooling and there is a low level of nucleation, you will end up with mortar structure. So what we have to do is increase the level of nucleation. As the level of nucleation increases, then there is no need for undercooling to happen. There is no need of that extra energy that needs to be drawn from the metal itself to form a stable nuclei, because you are going to provide external nuclei. So let's come to nucleation and inoculation. There are two terms here. One is homogeneous nucleation. That is, when the growth is initiated on this substrate, on this nucleus, having the same chemistry and structure as the solid which is going to form, then it is called homogeneous nucleation. And an example is, under certain conditions, graphite can nucleate on carbon-rich regions in liquid iron, and this we can treat as homogeneous nucleation. In heterogeneous nucleation, it occurs when you are providing the substrate particles deliberately from outside. They are introduced into the melt to promote the equiax grain formation. Automatically, there is no need of undercooling. The free energy requirements are already ready-made, particles where surface is already existing, solid has been introduced in the melt. So this is a common practice in liquid processing of cast iron. So because they are inoculated with specially designed alloys. So this is called as heterogeneous nucleation, is called as inoculation. I know these days the word vaccine and inoculation is in the minds of every one of us. So here we are talking about inoculating the iron and not inoculating people. But interestingly, the actions that will be generated in the human body with the vaccination and actions that are generated by an inoculating material inside a cast iron bath, they have a similarity. We are introducing a certain species and there are different techniques. We talk about Pfizer's vaccine and we talk about the COVID shield and all that. Each of them has their own different technology. What is the purpose of nucleation? It is pretty simple. It is to improve the metallurgical properties, that is, to increase the graphitizing tendency and avoid the graphite or carbide formation, cementite formation. It also improves the mechanical properties such as strength, hardness, in case of ductile ions, elongation, and machinability. That is the purpose. I'll repeat again. You use inoculation to ensure that the undercooling is minimized, the adequate number of nuclei which are available in the melt on which our friend graphite can precipitate out of the liquid ion that we are handling. So here are a few simple micrographs. If we don't inoculate iron, this is how the microstructure will look in gray iron. While well inoculated iron, you can see not a very great photograph, but it still shows you large, A type of graphite peaks. We have discussed this in our gray iron metallurgy. Then here is a microstructure for ductile iron, uninoculated. You will find a lot of carbides there apart from the blues which are present. While inoculated iron is here, is showing pearlite and ferrite, all those nice phases. Now, inoculation works in two phases. One, it gives nucleation. So, it nucleates the solidification to produce eutectic cells with graphite instead of carbide. Now, inoculations will create nuclei, and we'll see more about it. Here are a few words. They can be oxides and sulfides from a variety of elements which are presented. And the second important point is the growth. So, higher the number of eutectic cells growing on the nuclei changes, so that depending on what treatment you are doing, so growth is being governed by the modification which can happen because of the magnesium. You don't use magnesium as in gray iron and you will get A type of graphite. And to do good inoculation and you will have less amount of D and more of A. While when it comes to Hg iron, treatment with magnesium, we also call it as modification of the graphite morphology, graphite shape. So very quickly, processing of liquid iron is liquid is inoculated so that solid forms, and the process is you have these nuclei. In case of gray iron, you have initial cells growing in this liquid. They grow and finally they meet each other to form this A type of graphite structure. In case of ductile iron, where the sulfur is low, we have done the magnesium treatment and then done the inoculation. Again, nuclei present in the melt, initial graphite nuclei are forming here. We'll see a little bit later what type of sort of nucleation that you see in this case of eutectics is. This is known as coupled eutectic or coupled grain, where you have austenite and graphite growing side by side. While in case of Hg iron, you call it as divorced eutectic. That means austenite and graphite, they are not not like what you are seeing here in the gray iron case. They are growing separately. Again, those cells grow and then finally they meet, and this is the kind of structure we will get. On inoculation, we talked about undercooling and inoculation, and this was a slide which I had shown earlier as well. So, well nucleated inoculant, you have no amount of undercooling, good A type of graphite. If it is under inoculated, then you will get B type of structure where you will get undercooled graphite, finer graphite flakes and the center. either over inoculated or hyper-eutectic carbon. Too much of carbon, very little undercooling, while big undercooling when it comes to D and E type of graphite. You see those austenite dendrites, and in between the dendrites, you have this randomly oriented small flakes or oriented flakes in case of E. Few more pictures. You see the graphite nuclei here for eutectic solidification. So graphite nuclei, austenite is growing along with graphite. I'm not going into too much of details because Thiel would say that graphite is more faceted, so that actually grows first, and then austenite is growing along with that. This is coupled growth. It grows, and finally a eutectic cell of austenite plus graphite has formed. In 3 dimension, it may look like this. And then as the eutectic further freezes, if it is well nucleated, slow cooling, the austenite will, more carbon will come off as graphite, and then you will have ferritic leptallium. If the carbonic equivalent is low, still reasonably nucleated, and you have a composition which is slightly different. You have more carbide forming elements in the matrix like manganese in the melt. Then you would have ferritic ductile ion, but again nice flakes. And here is a structure of alternate lamellae of ferrite and cementite in twilight. Similarly, if you look at solidification of Hg ion, you have this what we call as a divorce eutectic. You have graphite separately, you have austenite growing separately. And as both of them, you will find there are these nodules, they are getting finally, as the whole of the melt is freezing, these nodules will finally become part of the structure in between the dendritic arms. This is how the graphite nodule is between, and this is how the microstructure. I had shared this in our Asian lecture as well. Now, let's look at what are the requirements of a good inoculant, an efficient inoculant. The inoculating material substrate must be solid in the melt. We are talking about heterogeneous nucleation. Its melting point must be higher than the melt temperature, and it must not dissolve easily in the melt. It is not as if it will never dissolve, but it will dissolve slowly. There must be a low contact angle between the metal and inoculant particles. That means metal should be able to wet the inoculant particles so that the effective nucleation can happen. The carbon atoms can get deposited onto the surface of the inoculant particles. Inoculant must expose a large area to the liquid. This means you need a good dispersion of inoculating particles in the bath, or by using an inoculant which has got inherently rough surface geometry. There is an interesting point on this, but which I may, if we get the time, I'll discuss it later on this geometry of the inoculants. This is in connection with leads to inoculants which are used for at the very last possible moment in the stream of the metal. But if time permits, I'll talk on that. Other requirement of efficient inoculant is that carbon atoms are supposed to attach to the lattice of this substrate, the inoculating particle. Ideally, the crystal structure of the substrate and the solid which is going to form on it should be same. That is ideally. That is, the lattice parameters should be very similar. The substrate must have one or more planes with atomic spacing and distribution which is close to that of one of the planes of the solid to be nucleated in this case. That means we are talking about either austenite coming out or graphite coming out, and their crystal structure, which we discussed in our first lecture. Here is a diagram which talks about this coherence. Here is the nucleant, and this is the spacing of the atoms on the this is the interface between the nucleant and the solid which will get deposited from the liquid. In this case, because these spacings are very similar, we are calling it as coherent interface. While in the second figure, there is bit of abnormality. They are not exactly the same, so we are calling it as incoherent interface. Mind you, this is the side on which the solid is, or from liquid the solid is getting deposited on this nucleant or inoculant. The inoculating material also should have ability to nucleate at very low undercooling. Here is another interesting thing. We saw these dimensions here. This dimension is AN, this dimension is AS, and this delta, which is called as linear dysregistry or mismatch. So what we are talking about is that the physical arrangement of the atoms in the nucleating material should be preferably as similar to the solid that it is supposed to solidify on its substrate. Now let's look at what are the inoculating materials, and the content that follows I have picked it up from an excellent review paper published in Material Science Forum in June 2018. The title is The Role of Compounds in Graphite Formation in Cast Irons. It's an excellent paper. Generally, special ferrosilicon based alloys and sometimes blends in the past at least were used as inoculating materials. So inoculants are mostly special ferroalloys or ferrosilicon alloys, and they contain the additions of inoculation effective elements which have high affinity for oxygen, which means calcium, aluminum, barium, zircon, strontium, rare earths. So they will form either oxides or silicates, as well as some inoculants may also contain bismuth, titanium, manganese, sulfur, oxygen, so that they can form sulfides as well. We'll see why. Inoculants which are based on ferrosilicon with additions of graphite are also available. In fact, in the past, what I call as blended inoculants were used. They were commonly made out of ferrosilicon with 70-75% silicon with some amount of aluminum in it and calcium in it. And then there will be mixtures of ferrosilicon granules with graphite plus calcium silicide for different applications. Many manufacturers, they will in their data sheets give what these blends are. But as the time progressed, we have moved on from using blends because of the inherent problems of variation in the mix that happens if there are mixes of granules to what I will call as alloy inoculants, which we described in the first bullet. One word, if somebody wants to use graphite as an inoculant, it must be crystalline graphite. That means HCP, hexagonal close packed structure. So it has to be graphite which is sourced from what I would call as electrode graphite, which forms at 2500 degrees centigrade. That's got the right structure. Because manufacture of these ferroalloys is a separate technology by itself, so I am not going to get into that. Only one word I would say is most of these good ferrosilicon based alloys from using variety of these other elements, they would be produced in submerged arc furnaces, and one needs to have excellent control over the operation of this furnace to get the right chemistry of these alloys, as well as you need to have the right kind of casting technique, because these inoculants are also cast as slabs. They are then cooled and crushed to the right grade. So that manufacturing of inoculants is another technology by itself. Last point, if you use extremely pure ferrosilicon without any of these other elements, it is not very effective. Now, how these special ferroalloys meet the requirements to be good inoculants? In earlier slides, we had listed out about 4 or 5 important points. So we will see that inoculant substrate must be solid in the melt, and its melting point must be higher than the melt temperature. So the chemistry of these ferrosilicon alloys is very crucial. The chemistry and the way they are solidified should be such that they will not dissolve very readily into the melt. They will gradually react so that they will give this inoculation effect. These special ferrosilicon alloys, they will form oxides and sulfides which are stable at cast iron melt temperatures, and these compounds, these oxides and sulfides, they serve as nuclei. In the paper which I referred, they have given lot more details about the free energy of formation of these oxides and sulfides and how they are in the negative region, so that formation of these nuclei is favored. Delta G is negative. There must be good wettability. There must be low contact angle between metal and nuclear particles. So above compounds have excellent wettability to the melt. Inoculant must expose large area to the liquid. And we said it can be achieved by producing fine dispersion of inoculant or by using inoculants with rough surface geometry. That means the way the inoculant is crushed is what will give us the surface area that is required for the inoculant particles. And large number of oxide and sulfide particles are generated when these ferroalloys react with oxygen in the melt and sulfur in the melt. Now, here is a very interesting graph about lattice mismatch. Because we talked about the stability of the inoculant and the nature of the inoculant, and other important parameter was the lattice mismatch. That is, we talked about delta percentage. And if we look at this graph, what we notice is, if this lattice mismatch is low enough, less than 6%, then you have got an inoculating particle which is very strong. And so the things that we see on this side, see the graphite has got the best match, the dysregistry, the mismatch is the lowest. So it is one of the best to have the nucleation. Then you have a range of them. You have the sulfides, and you have nitrides, and you have barium silicates, and you have got strontium aluminosilicates. Between 6 and 12% mismatch or dysregistry, it is medium level of medium level of inoculation ability from this point of view, lattice point of view. So a lot of these inoculants will then form under that magnesium sulfide and manganese sulfide and calcium carbide and so many of them. So let's summarize the role of oxides and silicates and sulfides in the nucleation of graphite ions. These are the complex compounds that act as nucleation sites in the commercial cast irons. And this process happens in 3-stage graphite formation, but it follows a different sequence for gray iron and HDI. First, the initial reaction is oxide and silicate in gray cast iron, while it is sulfides in ductile iron. Mind you, we are doing magnesium treatment and we are generating magnesium sulfides in ductile iron. The second step is a second compound nucleates on the first one. That means in case of gray iron, on the initial oxides and silicates, you will find that a complex manganese sulfide gets deposited, while complex silicates gets deposited in case of nuclei in ductile cast iron. So they are reversed. It is oxides followed by sulfides in the iron, and sulfides followed by oxides or silicates in ductile iron. And graphite nucleation on the sides of the stage 2 compounds happens, which have low crystallographic misfit with the graphite. We have already seen in the last graph the misfit or mismatch or dysregistry for these compounds. And on these compounds then, though I have not included a slide here, in our previous case, both in gray iron and HE, we saw how the graphite grows either as a rosette in case of gray iron, that the growth is happening on the face planes of these sort of hexagonal structures which are present, while it happens perpendicular to the base planes in case of ductile iron. And then resulfurization by using manganese sulfur ratio control, preconditioning with strong oxide forming elements, either aluminum or zirconium, large lumps being used in, we will look at preconditioning a little bit later. More potent inoculants which contain sulfur and oxygen and oxysulfides, that becomes very beneficial in giving inoculation treatment effect in critical solidification conditions. That means in adverse solidification conditions also, good nucleation will happen. Now, what are the inoculant types and how do we go about selecting this? And this is picked up from a nice paper on inoculation of cast irons. We can already say that ferroalloys with these kind of compositions, strontium, barium, cerium, lanthanum, or even calcium silicide, zirconium, manganese zirconium, standard ferrosilicon, but with aluminum and calcium. These are all the ferroalloys which are used for inoculation, and there could be many more, like we said. Bismuth also gets used in some cases. And down below I have shown graphite or a blend of ferrosilicon and graphite. Many of them would be produced in submerged arc furnaces. Usually the manufacturers or suppliers of these inoculating materials, they will give composition range as well as size grading and recommendations how to use them for their respective sort of brands of products. Now, another important thing that we have to recognize is the fading effect of inoculation. Now, because these nucleic particles inside the melt, do they remain all the time? No. Their effect is transient. So it depends on the treatment temperature, but most of all on time for which they are present in the melt. And this particular changing effect of the inoculating materials is called as fading of the inoculation. The fade time begins when you have just added the inoculant, and it ends when the eutectic solidification temperature is reached. When there is less number after adding the nucleating material also, there could be agglomeration happening, thereby the number of nuclei can become less, or reoxidation can happen, or some nuclei may get dissolved, and so there would be a reduction in number of nuclei all the time. Here I am not going to talk about critical radius for a nuclei to be stable. That is part of the solidification process itself. There is something called critical radius for these particles which are forming nuclei, they remain stable only if that radius meets radius. Anything below that gets dissolved by the bombardment of the liquid molecules which are roaming around in the liquid metal. The fading effect depends on the composition as well as the size grading. Another important point is very powerful inoculants in terms of their chemistry also tend to subside very quickly. So their effect goes away quickly. That is a word of caution. Very long lasting inoculant effect is given by normally the inoculants containing barium and cesium because their oxide sulfide they tend to last longer. So when we do the inoculation process per se, we need to remember these important factors connected with fading of the inoculation effect. Another aspect to be considered is the wall thickness of the casting. Apart from the pouring temperature, we have to look at the wall thickness. So normal wall thickness areas of the casting, say from 5 mm to 50 mm, they will solidify within few seconds to few minutes. While if the very thick sectioned heavy castings, wall thicknesses which are bigger than 60 mm, they may take much longer to fully solidify and recrystallize and all that. It can take hours. Big 2-ton weighing, say, components for windows or big machine tool castings. There, you will always find that fading effect happens in bigger castings because there are less number of nuclei. Because they are less in number, they tend to grow bigger. Sorry. Like in case of large ductile, so we'll have lesser nodule count, but large nodules. Similarly, low cell count and large grains in case of gray iron. Now, what are the different aspects that one or factors that one has to consider while selecting an inoculant? One is whether we are going to nucleate gray iron or we are going to nucleate He iron. That is one part. And what grade of iron? Is it going to be low grade iron, grade 150, grade 2, or it is going to be high grade 250 grade iron or even higher than that? Because the chemistry of the iron will change. The charge makeup will change, and so the incipient nucleation levels will change. So how powerful an inoculant you will need will be decided by this. Then we have to consider the section thickness and size of the castings. We talked about this point earlier, base metal chemistry, which depends on what grade you want to produce. Then another important point from timing point of view and temperature point of view is plant layout and operations. So how many number of transfers of metal are happening from furnace to the actually pouring of the mold? Or what is the way the plant is operating, or are there breakdowns and there is holding time for the metal? Or there is a long travel for the metal, distance to be traveled. That is what decides whether you have to do a single stage inoculation or you have to do this dose of inoculant at 2 stages. The type of pouring system that is used, is it ladle inoculation, is it tundish? Now, more automated plants, you are having either a tundish pouring or press pour or more automated ladle pouring or manual ladle pouring. What is the size of the ladle and quantity of metal being treated? What is the location where you want to inoculate? These are all the factors which will then decide what is the chemistry of the inoculant that you will choose, what is the size grading of the inoculant that you will use, and at what location and in what manner you will add inoculant into the ladle. if there is any inoculation dispensing device, is it going to be just that somebody takes up a spoonful of inoculant and adds it as the stream of the metal is being poured into a ladle or being transferred from one ladle to another ladle? Or is there a mechanical device which is actually adding the inoculant into the metal? How much to add? And the simple answer is the lowest possible amount for successful inoculation. What size? So you choose the size which ensures that inoculant dissolves a little bit, but not fully, but it has a feed resistance, and when to add as little as possible. And in the previous slide, we said where. It all depends on your variety of factors that we considered earlier. Quantum of inoculation, very quickly, few points. When do we need more inoculation? We need more inoculation when carbon equivalent is low, or sulfur levels of your bath are low, or there are high level of chromium, vanadium, carbide stabilizing elements present in the charge. You have induction furnace melting, where because of the churning there is, the less number of incipient nuclei. Or if you are using automatic pouring furnaces like press pours, the holding time of the metal bath goes up. That means there is fading of inoculation happening, so we need more inoculation. Higher temperatures again, because there will be dissolution of inoculants, fade will be more, or you will need more quantity. When there is a faster cooling of the casting, here we are talking about nature of casting, thin-walled casting, then in order that well before the metal freezes, you want carbon to come out of the solution. So you want to provide more number of nucleation sites in the bed. If it is ladle addition, again you need to add higher quantity, higher percentage of inoculation. Or if it is large casting, you need long field times, you need more inoculation. You need less inoculation when you are using high carbon equivalent iron. There is a very low content of alloying elements, typically in cupola melting. Inherently, the incipient nucleation level itself is high. The inherent nucleation level is high. Or in your induction furnace, you have a charge mix which has got higher pig iron and then again the inherent nucleation level will be high. Or there is high silicon in the gray iron again. If you are making that type of casting, again the nucleation levels will be high. If there is going to be relatively slow cooling, then again you will need less inoculation. And if the cooling is going to be faster, I have already mentioned short field time, less inoculation, or short cooling times, I should say. Method of inoculation. We have already considered these factors. Inoculation effect is direct correlation to the previous history of the metal. That means composition, the initial state of nucleation, temperature, time. It can occur in several stages, but the greatest impact of inoculation is just before pouring. During pouring, if we add inoculation, we will get the best out of the inoculation. Then depending on the nuclear effectiveness and cooling conditions, sometimes inoculation may take place in the furnace or in the intermediate vessel, or preferably during the pouring of the metal inside the mold. So we have ladle inoculation, we have preconditioning, that means you are adding your lumps. In this case, I am using my words carefully. It is much coarser inside the furnace itself. Or late nucleation, it can be either in the late stream, just as the metal is getting poured, or even later, which is inside the mold, or you are using cored wire inoculation. Again, instead of stream, a powder flow is going, you are adding the metal powder, which is the inoculant powder, which is inside a cored wire. Very quickly, what is preconditioning or pre-inoculation is addition of preconditioning agents, that is various alloys that we discussed, which have nucleation effective substances early in the furnace or during tapping. This enables or it makes favorable conditions for getting the optimum structure or graphite formation. So lumps containing variety of these elements, cerium or zirconium or manganese, barium or aluminum, they are used as preconditioning agents. They contribute to reduction of oxygen content because they get oxidized and form these nuclei in the bath, and they improve the distribution of the nuclei. We are doing it at first stage in the melting and pouring cycle. Sometimes people will use silicon carbide. That also can be looked upon as not only adjustment with silicon and carbon, but provision of nuclei. In later nucleation, as the picture shows here, inoculant is added during the tapping or cooling. In this case, say for example, after magnesium treatment, you are doing the cooling, or you are transferring from your treatment ladle or converter into a transfer ladle or a pouring ladle. So depending on the amount of iron, the right size grading, typically the grain sizes ranging between 0.6 mm to 6 mm are used for this type of inoculation. And for different suppliers offer different ranges, 0.6 to 2 mm to 6 mm, depending on each plant's operating conditions. Avoid putting the inoculant at the bottom of the ladle, but preferably add it into the stream of the metal. I remember in my old days in Foundries, we sort of making a packet of inoculant and just throwing it at the bottom of the ladle just as the tapping was starting. That is perhaps not the best way of doing it. And inoculation addition quantity or percentage depends on how much metal you are doing, how potent your inoculant is. Core wire. Here the inoculation is performed with the help of wire which contains granular inoculant inside the myostream wire. And here is the setup that I have shown. You have this spool of core wire, it is being fed through the feeding or guiding tube into the ladle. Wire is fed into the melt via controllable feeding mechanism. So there is a precise dosing of inoculant. Like we discussed in case of magnesium treatment using core wire, depending on how much you want to put in, then you will adjust your so many feet per minute kind of feed rates, so many meters per minute per second. Wire inoculation can be done both in ladles as well as in pouring channels or pouring launders in our furnaces. Here is a picture of lead stream inoculation. So inoculant is added into the metal stream as it is getting poured in the mold. You see the stream of inoculant here. In most cases, stream inoculation devices are used. They enable the quantitatively uniform addition of inoculant to the pouring stream over entire casting process. Typically, for these machines, you will adjust the cycling that inoculation feeding starts just after the pouring has started, and it stops just before the pouring is stopped. So the dosage of inoculation is programmed into the device accordingly. Here, typically for stream inoculation, sizes between 0.2 to 0.7 mm are used. The amount added should not be more than 0.15 because we are doing late stream inoculation and we have to ensure that the inoculant dissolves in a very short period of time. So if excess addition happens, you will get inclusions because of undissolved inoculant. The advantage here, of course, compared to ladle inoculation is late addition time, chances of fading are next to nil. Mostly used with automotive automatic cooling systems. I've taken this picture from metal stream inoculation system of Mexico. So you have this control unit with microprocessor which sits slightly away from the metal. This is your kind of hot box, so to say, dispensing unit, which contains the hot hole over here. And inside there is a slide gate arrangement. Like this, where the feeding is by gravity, people also have screw feeders for doing the slave stream inoculation. Quickly, a word about in-mold inoculation. This is the last possible stage where you can add inoculant. The inoculant is introduced into a chamber in your running system, or sometimes it can be introduced into a pouring basin. You may recall that in SGIM, when I had talked about the in-mold treatment, I had shown a typical layout of the running system where you have a chamber in which your magnesium alloy is put. Here, you put the inoculant in the running system. I remember in the old days when Tata Motors used to put a tablet of inoculant in the screw well as the in-mold inoculant. The advantage here, of course, is that that there is less contact of air and the iron directly flows over the inoculant all the time through the entire pouring cycle. Instead of compacted powder forms, the cast inoculant blocks are also used so that the risk of undesired inoculants going into the running system and going into the casting and its associated inclusion related problems will not happen. Couple of graphs on this. I have picked it out of the literature given by ASK. In fact, long ago I happened to visit this plant which produces these cast inoculants, mold inserts as they call it. Now here is a diagram, or here is a graph that they provide for dissolution time for these shapes versus the pouring time for the iron, based on which you can choose what size of the cast block you should use for doing the inoculation. This is for smaller pouring times, smaller castings. For bigger castings, you have your pour weight here on the x-axis, so 1 ton and 10 tons and even more. You have your pouring times and you have your dissolution times and the selection of either the baffles or these cast ingots. I'm calling them as tiny ingots. And these can be embedded either in the pouring basin in case of large casting or in a cavity in your running system. Now, checking the effectiveness of inoculation. This we have covered in our earlier lecture in gray iron also. Wet chill is very, very popular. And as you can see, it sort of reproduces in a very nice way what is likely to happen in actual casting with variety of section thicknesses. And I'll not spend really too much of time on this. We are running out of time now. Cooling curves, use of thermal analysis, another technique for assessment of solidification, as well as effectiveness of inoculation. I have talked about this in the past also. And precaution, that long delay between pouring and thermal analysis will give wrong results as a quality control tool because fading effect will happen. Very briefly, casting defects and inoculation. Now, here are a few. Improper microstructure, which is graphite type or grain size, cell count, module count, and then improper mechanical properties, or I can summarize as high section sensitivity. That means you have a casting where you have a big mix of thin and thick sections. And if your inoculation is not proper, then you will get vastly different microstructure in two different sections of the casting and different properties, and that may become a problem. Or say low nodule count in case of large iron castings, sometimes nitrogen fissures, chunky graphite in case of large ductile iron castings, where there is a degeneration of nodules which can be happening because of longer cooling times and nucleant or inoculant not being effective for that type of situation, or inability to achieve the, say, a graphite flake type, A4, A6, say, in engine blocks. So again, what you are looking at, whether the choice of inoculant is right or not, whether the place of inoculation is right or not. And this is as far as inoculant is concerned, whether your dispensing unit is working well or not. Many times in automated foundries, if the inoculation device is not working well, from mold to mold there could be variation in the dosing which is happening inside. So doing proper calibration of the inoculating equipment is very crucial to avoid these improper microstructures or getting inclusions. Your settings are not right, your measurements are not correct. So you over inoculate and land up with inclusions. Or you over inoculate and there are too much nuclei which results in micro shrinkage, and as can happen in cylinder heads, leakage during pressure testing. That can happen. So then you have to look at your inoculation practice, look at what kind of inoculant inoculation you use. So strontium-based inoculants are pretty popular for avoiding these micro shrinkages. See, here you are balancing the two things. There might be a slight drop in the strength because the grains are a little coarser, but then you are avoiding the shrinkage and you are still within your mechanical property requirements. That is what will happen when you are using strontium. While if you are using another type of inoculant, maybe something like zirconium containing or barium containing inoculants, late stream applications, and you may find that while you are getting good strength, or rather too much of strength on a higher side, and you land up with microstructures. Inclusions we have already talked. If the inoculation is not proper, undercooling is happening, carbides will appear, and you will get poor machinability. Your graphite will not be proper, or sometimes you may get too much of D type of graphite, which is excessive ferrite coming out, and again you will have problems in the machine. Sometimes there can be pinholes which are linked with buildup of aluminum in cast metal, especially if you are using inoculants which have higher aluminum content. So that is another thing that people check in these cases. I think we are going to run out of time. I've taken this picture of intrusions in ductile iron to show that what can happen. Thank you very much. I would have loved to have more time to discuss about late stream and many other things, because there are situations where everything else in terms of your chemistry and composition and inoculation looks good, but in a spread of castings, you may find different castings are exhibiting different microstructure.
Thank you for the
Thank
presentation,
you very much.
giving answers to why, when, where, and how of the inoculation process. Surely the attendees have now know the rationale behind the processes and actions they perform on the shop floor. Thank you again.